Hello, good afternoon.
Good evening, sir.
Good evening.
Kalyani madam.
Sir?
You can start.
Okay, sir. Good evening, everyone. We are honored to introduce Dr. Jaume Anguera, IEEE Fellow, renowned antenna technologist and the founder and CTO of Igneon Barcelona. A global leader in miniature antenna innovation, he is the inventor of over 215 granted patents, with his inventions integrated into more than 200 million devices worldwide. His groundbreaking antenna booster technology, the foundation of Igneon, has transformed wireless connectivity for the IoT devices through ultra miniaturized antenna components. Dr. Anguera brings over 26 years of R&D excellence, having contributed extensively to antenna design for leading global companies, including work in South Korea with Samsung and LG during his tenure at Fractus. He is also a professor at Ramon University, a member of Smart Society Research Group, and the author of more than 310 highly cited publications, 8 books, and numerous internationally recognized research contributions. His work has earned prestigious awards, including the IEEE New Faces of Engineering honor and recognition as a finalist for the European Patent Award. A respected global educator, Dr. Anguera has delivered more than 90 antenna courses across the world and supervised around 190 master's and doctoral theses. He serves as associate editor of the IEEE Open Journal of Antenna and Propagation, and as an IEEE distinguished lecturer, he continues to inspire the next generation of antenna innovators. We are privileged to have Dr. Anguera with us for our FDP on V2X beyond 5G trends, technologies, and future directions. Over to you, sir. Thank you, sir.
Thank you very much. First of all,
So you can share, sir. You can share the screen.
yeah, let me share my screen.
Yeah.
And let me know if you can see my slides. Can you see my screen?
Yes, sir.
Okay. So, good evening, and thank you for inviting me. It's really an honor from Barcelona, Spain, to share to you about antenna booster technology for the V2X communication. I'm Jaume Anguera, a professor at Universitat Ramon, as well as founder and CTO at the company Ignion, both institutions in Barcelona, Spain. In today's journey, we are going to understand about this technology. It's not that I'm going to talk about how to design antennas, but more importantly, I'm going to share how we can design devices that may be useful for this V2X kind of scenario, where we'll have protocols for LTE, for the 5 gig, all these kind of frequency bands, GPS combined with GPS combined with Wi-Fi. So how this technology is simple to be used to design devices, as you can see on the screen, to provide connectivity. So I'm touching several aspects in this lecture. So hopefully any of those is attractive for your research, or perhaps if you are working with a company that is useful for you to provide connectivity to any kind of wireless device you are dealing with. Well, this V2X, is connecting cars with traffic lights, car with pedestrians, car with bicycles, car with infrastructure. So at the end, it's amalgam of plenty of devices, plenty of protocols, some of them at 5 gig, others in combination with other antennas in LTE or GPS and so on. So at the end, antennas are everywhere in this kind of V2X scenarios. And in particular, I'm focusing on those small antennas, not big arrays for the infrastructure, but those antennas in small devices. Perhaps antennas that can be embedded in a bicycle, or perhaps antennas that should be embedded in a tree, perhaps, or antennas that can be embedded in a traffic light, okay, to provide connectivity to the car. And those antennas should be small, obviously, because you have to integrate in a tiny space. Also, they should be efficient. The efficiency of the antenna at the end ensures that we have range of the connection and also compatible with low cost. Okay? Cost is also an important aspect that we should take into account. And at the end, this is also combined with IoT. Everything as parking sensors as well can be connected with cars. And these parking sensors at the end are connected to the cloud. So V2X is at the end, it's part of the smart city, part of the IoT. So let me highlight here some numbers for IoT only. For IoT, you can see in this slide the forecast for 2030, how big is the number of connections that we are going to have, about 30 billion of connection. This is huge. This is why this topic is so important, because it pushes industry, it pushes research institutes, it pushes academia to work at several aspects, not only protocols, not only transceivers, but also at the RF part, designing efficient antennas to be embedded in this kind of devices. And this is where I will focus my talk, mainly in the connectivity, to provide connectivity into wireless devices. So let me jump now into more technical stuff. To be illustrative, in this slide, what we have is antennas used in mobile phones. Those antennas typically are placed on top or bottom of the mobile phone. And what I want you to focus is that, well, these shapes, which at the end are conductive parts, no one is the same. Although the mobile phones may look more or less the same form factor and even the same frequency bands, the antenna is not the same. Why is that? Well, perhaps the mechanic is different. Sometimes you need more space, less space. So at the end, we have different kind of geometries, different kind of antennas that in terms of efficiency, bandwidth, and so on, these antennas are efficient. They provide the bandwidth. But you can imagine that if for every single project we need to start from scratch, this is not efficient in terms of the time you have to invest or resources. This technology, this antenna technology, is based on shaping the geometry of a conductive element. So based on the shape of the conductive element, you can design your antenna to operate at the frequency you want. This is what we call self-resonant antennas, okay? So here we have another example. On the left, you can see this kind of antenna, conductive element with a very sophisticated shape in order to make the antenna small, so the antenna can be encapsulated in a small space of the mobile phone. And also they have several branches because the antenna in this case has to be multiband for 3G, 4G, whatever. So back in 2003, 2006, when I was working in South Korea for the big OEM, Samsung and LG, we were doing this kind of antennas. And the pain is what I said before. You need to start from scratch for every single device. So our vision back in 2007 was, well, can we do something in a different way? So we don't need to design a different antenna for every single device. So can we design something that it's always the same, regardless the PCB, the printed circuit board size or the frequency bands? And the answer is, well, our hypothesis is maybe we can do something by using a tiny element that can excite the ground plane of the PCB. So the antenna is not this part here, but we convert the ground plane to be the antenna. So we can excite the ground plane by use these tiny conductive elements that we call it at that time ground plane boosters, because it boosts currents on the ground plane. Now we call it antenna boosters to simplify the name. And in all scientific papers that we have written, we use this terminology. However, in 2015, since we saw that this has a huge potential application, we created the company Ignion in Barcelona, and we call this technology, from a commercial standpoint, virtual antenna technology. But in this presentation, I will try to always to refer as antenna booster, but if you see sometimes virtual antenna, this is the commercial name, and the technical name for this technology is antenna booster. So let's understand how a tiny, a very, very small component can provide connectivity into a wireless device that eventually can be embedded into a bicycle, into a traffic light, into, for instance, a parking sensor that has to be connected to a car, or even in a transmit control unit embedded into a car. Well, just for your reference, these are the first patent publications that we got granted. So we are happy that after strong research, this came into light. So we are happy that these patents from 2008 at the end were granted 4 years later. Now, let me highlight a simple, but I think very interesting evolution of antennas for wireless devices, from the very well-known external single band antennas, okay, typically for 900 or whatever. It's a single stride component, and with large volumes. You can imagine if it's for 900 megahertz, this is almost 100 millimeters, an external antenna, easy to steal, easy to break. The first internal antennas appeared by 1996, but, well, you can see still they rely on shaping the geometry of the conductive element, and as the time goes by, the volume of the antenna decreases, okay, but still you can see that it relies on, again, self-resonant structure shaping the conductive element to obtain single band or multi-band operation. However, the big breakthrough in miniaturization is with the apparition of this antenna booster. Let me show you in my hands to see how small this component is, and the one I'm holding in my hands is useful for providing connectivity in 4G frequency bands, 800, 900, 2 gigahertz, 2.5, and so on. Okay, so in terms of volume, it's only 100, less than 100 millimeter cube. So it's a small component, so very convenient to put in a small PCB in a bicycle, for instance, that has to be connected to a car, for instance. Okay, so in summary, antenna boosters are very small components able to excite the PCB to make the PCB the antenna. They are off-the-shelf components, so easy to assemble into a PCB like any other chip, like an amplifier or a filter and so on. And they can support single band or multi-band across any protocol, living or sharing also with V2X protocols. So the architecture is very simple. On one hand, we have the antenna booster on the PCB. This is a simplistic view of a PCB. You have the ground plane populated of transceivers, batteries, and other chips. So we have the antenna booster. Then we have a matching network. I'm going to explain why the matching network is so relevant in this antenna booster architecture. And then we have the ground plane. And the ground plane plays a very important role to provide efficiency and to provide bandwidth in the application. So 3 important ingredients: antenna booster, the matching network that is connected to the transceiver, to the RF module, and the ground plane. So let me put a metaphor on how can be that a small antenna booster can excite the ground plane or can enhance efficiency in a PCB. Well, let's use this example of the acoustic drum. An acoustic drum we have the drum stick. The drum stick obviously pushes the membrane. So as the membrane vibrates, it pushes the air and it creates sound wave. So the sound waves are in somehow created by the vibration of the membrane. It's not because the drum stick is generating waves, okay? The important role of the drum stick is to push the membrane, in this case, in the central of the membrane, in the central part of the membrane. Because if you push at the boundary, obviously, you are not going to make any vibration, so you are not going to create sound wave. So this means that the membrane is relevant to create the sound wave, but the drum stick is important to generate or to push the membrane. Okay, so in the same way, the ground plane behaves as the membrane and the antenna booster behaves as the drum stick. So depending on the position of the antenna booster along the PCB will enhance currents on the ground plane that at the end will ignite electromagnetic waves. Okay, and the size of the antenna booster can be very small. The same way as the drum stick, you don't need a 1 meter drum stick to make strong noise. If the drum stick is big enough, at the end what matters is the size and the quality of the membrane, the same as happened here. Now let me illustrate the different approach when designing connectivity into wireless devices through the conventional antenna approach by using self-resonant antennas compared to antenna boosters. In this case, we have a ground plane, we have a monopole kind of antenna, which at the end is a metallic component, in this case, this blue trace, and then we have the RF source. Typically, this is single band. In this graph, I'm illustrating frequency on the horizontal axis, and in the vertical axis, I have efficiency, so from 0 to 100%. This efficiency reflects how much power is radiated into space compared to the power that the transceiver delivers to the antenna. So if the efficiency is 100%, this means that all the power from the transceiver is radiated into space, which is the convenient case. So 100% is good, 0% is a disaster. Okay, you don't have range, you don't have connectivity. So in this case, you can see the pink line illustrates that we have high efficiency in a single band around 900 megas. What if we want to create a second frequency band? Well, we need to sophisticate the antenna, perhaps by changing the geometry. In this case, we add a new branch compared to this one. And in this case, you have the first band around 900 megas, and then a second frequency region around 1.8 up to 2.3, 2.4 gigahertz. And last but not least, imagine we want to expand bandwidth at the higher frequency bands. Well, you need to sophisticate the antenna, perhaps by adding a parasitic element, slots. So you can imagine this is kind of a complex, iterative, and a process that also requires antenna expertise. You have to be an antenna expert to do this kind of designs and to have a lot of experience of designing this kind of antenna. Now you can see we have a first frequency region, and then we have expanded the efficiency up to 2.8 gigahertz. So what happens if we have to address these scenarios with antenna booster technology? Very simple. We have the same antenna booster on the PCB. So for the first case, which is single band, we have a simple matching network. So we have the antenna booster, and before connected to the transceiver, we have a matching network. Typically, if it's for single band, two components, two inductors, two capacitors, or one inductor capacitor, whatever, it's enough. So this is very simple. If we want to have multi-band, well, again, we keep the same antenna booster, and the only thing we change is the design of a matching network. In this case, more components because we need to have more band. And the last case, again, since we need to expand bandwidth, we need perhaps a more sophisticated, yet only 6 components in the matching network. So you can see this approach looks like more a microwave problem than an antenna problem. And one of you can argue, okay, yeah, Jaume, but now here in the left part, the complexity relies on designing the antenna. Now it's true that the antenna booster is always the same and it's very simple, but now the complexity is in the matching network. Say, yes, you are right, but designing these matching networks, it's so simple and fast that this is not a big deal. And why is that? Because any microwave solver, microwave office from Cadence, ADS, from Keysight, Ayun, Obtenilab, can design the topology, the values, and even with commercial values of this topology in less than minutes, based on genetic algorithm optimization or this kind of optimization procedures that is very, very simple and fast to design this kind of matching networks. So you can see that this approach enables a democratization of designing devices through antennas without being an expert on the antenna part. So this is very convenient for antenna guys, microwave, wireless engineers, hardware engineers that they don't have the antenna expertise. Let me jump into some fundamentals. I'm not going to be very detailed, but at least to provide for those of you, if you want to research in this topic more from the physical side, I think it's good that I share some highlights, okay? In this case, I told you before that the position of the antenna booster matters. So in this example, I have an antenna booster, a metallic cuboid of only 5 by 5 by 5 millimeter, very small, connected to the ground plane through, well, via an RF source at the corner of the ground plane. In this case, we have the same ground plane, the same antenna booster, but in this case, is connected to the center of the long edge. So we can take any simulator, CST, HFSS, FECO, whatever, to simulate the input impedance from, let's say, 0.8 gig up to 3 gig, 5 gig, whatever. And from the real part and imaginary part of the input impedance, we can obtain the bandwidth that one should get if we match the antenna system with a matching network, okay? And this line reflects the bandwidth we can get, okay? The continuous line is for the antenna booster at the corner, and the discontinuous line represents the booster at the center of this edge. In the low bands, 1 gig more or less, the bandwidth we get for the antenna booster at the corner is 20%, much more than the bandwidth we get when the antenna booster is at this position. And why is that? Well, the same as if you push the acoustic membrane at the boundary, you cannot make noise. In this case, a similar argument applies. But in this case, we are not talking about sound wave. We are talking about electrical field mode distribution in the PCB. So for the fundamental mode, this is the mode that we are exciting in this frequency, the electrical field distribution for the first mode has a maximum of electrical field at the corner of the ground plane and a minimum of electrical field in the center of the ground plane. So that's the reason why at this frequency of around 1 gig, 900 megas, if we put the antenna booster at the corner of the ground plane, we are at a maximum of electrical field. And for this reason, we can make the ground plane resonate. What we can make, or better than resonate, we can excite the ground plane. As a result, bandwidth is large. But if we put our antenna booster in a minimum of the electrical field, we hardly excite currents on the PCB. As a result, the bandwidth is very, very small, okay? This doesn't happen in other frequencies because in other frequencies, there are other modes that you can excite. In this case, this position is not bad because you can find modes that precisely in this position, there is a maximum of electrical field and you're exciting, in this case, another mode number 4. So eventually you will have bandwidth. But typically from a practical point of view, practical standpoint, corners are the best positions to get best efficiency and bandwidth design. If you do that, you can excite currents on the ground plane. This is a tiny antenna booster of only 5 by 5 by 5 millimeter. In terms of lambda, it's lambda over 50, so pretty small. But since the ground plane is not small, then as a result, the efficiency we can get is very high, around 80–90%. Okay. These are real examples of devices you can find for IoT. And for this red component, it's an antenna booster. Okay. By the way, this is from Cadley Wireless. It's a company from India where they have a narrowband IoT, LTM, antenna booster, a matching network, and the transceiver connector. As you can see, always the antenna booster is placed typically at the corner or fed. In this case, it's not at the corner, but is fed close to the corner of the ground plane. Okay, so this is a practical rule of thumb. Feeding the antenna booster on your device, it's the most recommended situation to get more bandwidth and more efficiency. Other positions obviously can work also if needed. Now we have solved the problem of efficiency. We know that if we put our antenna booster at the corner of the ground plane, eventually we can excite currents, but we have to deal with, okay, but the antenna booster will be connected to a transceiver. And those transceivers in this world of cellular connectivity, Bluetooth, GPS, Wi-Fi, including all the protocols for V2X, all these transceivers, typically they feature input-output port of 50 ohm. So what happens if my antenna booster, which by nature is not 50 ohm, is connected directly to my 50 ohm transceiver? Well, let's see what happens. In this case, this blue line represents the input impedance of the antenna booster. You can see the antenna booster at the corner, fed with a 50 ohm transmission line, and the impedance at the low bands of 0.9 gig, it's very far away of the 50. So this will create mismatch. This means that not all the power from the transceiver will be delivered to the antenna, so we will have poor efficiency. So the question is what we can do to our antenna booster system to transform this input impedance for the frequency bands of interest to be as close as the center of the Smith chart, as close to 50 ohm as possible. So very simple, by adding a matching network. Can be a passive matching network or can be an active matching network. I'm going to share some examples of both. So we have our antenna booster in the ground plane. Then we have our transceiver with the RF source, the internal impedance that transmits power represented in blue, so available source power. So the mission of the matching network is to minimize the reflected power. So eventually all the blue power is transferred to space. It's radiated into space. As long as the matching network does not introduce losses, this is something that if there is proper matching between the antenna system and the transceiver, we minimize S11, and at the same time we minimize losses, so we maximize the power transfer into space. Let me put an example. Here we have an antenna booster, only 12 millimeter, which represents lambda over 30 at the frequency of 900. We fed with an RF source. Yellow is the ground plane, green is typical substrate, FR4. So we have the RF source in this area. The input impedance is very far away from the 50 ohm. 1 and 2, it's 900, more or less. You can see in this graph, which represents S11 in dB. 0 dB is a disaster, -6 dB is not bad, -10 dB it's better. So you can see 1 and 2, it's very bad matching. But by adding a matching network, in this case only 3 components, 2 inductors and 1 conductor and 1 capacitor, sorry, we can transform impedance 1 and 2 to be close to the center of the Smith chart, close to 50 ohm, and as a result, the S11 now is below minus 12 dB. This represents a very good match that shows that all the power from the transceiver is delivered to the antenna system and then eventually goes into space. So you can imagine now, well, if we need to operate another frequency band, 4 gig, 5 gig, whatever, the mission is to design a different matching network. Let's see some examples. In this first case, we have the previous example. We have the antenna booster, only 12 millimeter, connected at the corner because it's the recommended position. We have a ground plane. In this case is a bare PCB, okay, for illustrative purposes. But in this PCB, you may have all the ICs, all the chips, the batteries, whatever is needed to provide connectivity and operation. And then the matching network should be around this area. In this case, with only 2 components, we can have high efficiency, which is this blue line. It's the measured efficiency in an echoic chamber, around 90% for frequencies in the 900 region, okay? Now imagine that we want to have not single band operation, but we want to have also operation in the 2 gigahertz. So we keep everything the same. In this example, everything is the same, antenna booster and so on, but as I told you before, now we only need to change the design of the matching network, in this case, 5 components. So we have a first frequency region with high efficiency of 70% at around 0.9 gig, and a second frequency region between 1.7 and 2.2 with efficiencies reaching 90%. And again, it may look complex to have 5 components, but it's not, because this is automatically obtained through optimization, okay? The only request for the solver is, as an input data, the input impedance of the antenna booster with no matching network, and the software will be able to provide the best matching network, even several candidates, that reaches your target. And if not, the closest to your target. So this is something that, well, this is the best I can reach. So it's also useful information because you know that there is no more that you can go beyond, okay? Yet another example. In this graph, you can see that the efficiency is starting to decrease from this point, 60%, and drops to 30% at 2.5, and eventually goes down. What happens if I need to have operation up to 2.7 gig, okay, for cellular communication? In some protocols, you need to go up to 2.7 gig, from 1.7 to 2.7. Well, in this case, you see, everything is the same. Antenna booster, matching network here is a 50 ohm transmission line for testing purposes. In a real device, you will have here the transceiver. And in this case, we have 1, 2, 3, 4, 5, 6, 7 components. And now the efficiency in the first band, 80%. This is measured data. And now you see that not only we have high efficiency up to 2.2, but also up to more or less 2.7 gigahertz. So we have expanded the bandwidth by designing a new matching network. Obviously, there are some physical limitations. You cannot expand the bandwidth more and more and more. Okay, this is known as the Bode-Fano criteria. Okay, that there are some physical limitations. The bandwidth you can expand by adding a matching network. But you can see the beauty of designing connectivity from single band, dual band, or triple band to multi-band by only changing the matching network, that at the end, it's simple and fast because this can be totally addressed by software. Yet another example in some applications for those of you working with perhaps MIMO. Well, we can combine antenna booster with MIMO. In this case, this is a simple example of having 4 antenna boosters at the corners of the ground plane to maximize bandwidth and efficiency. And in this case, it's for multi-band MIMO across cellular frequency bands. You can see here the frequency range of interest. The matching network is represented here, which is shown in this component. So you have the antenna booster. So this matrix here is the input impedance of the antenna booster on the ground plane without matching network, then it comes the matching network, and then it comes the 50 ohm port, which should be at this level. This line here is the 50 ohm transmission line to test the efficiency across all ports. Okay, more details you can find in this paper at the European Conference, okay, of antenna propagation. Let me move and let me just highlight, if any of you also is working in tunable components, how we can leverage reconfigurable components or reconfigurable matching network with antenna boosters, and why we need to do so. So far, we realize that we can have a matching network to expand our bandwidth, but in some situations, if there is no enough bandwidth, because, well, we need to cover more bandwidth than the one we can cover with a passive matching network, the answer is, well, what we can do? So the answer is, well, if a passive matching network cannot obtain the bandwidth we need, we can include in our matching network tunable components. And let me share with you two architectures. In the first one, we include a DTC, which stands for digitally tunable capacitor. At the end, it's a capacitor that can be software controlled, and it's an array of capacitors. So from, let's imagine, 0.4 pico up to 1 pico with steps of 0.05 pico. Okay, so at the end, you may have up to 32 different states. It's like having 32 different capacitors that you can control, and you can change the value of this capacitor. And I will put an example. And the other strategy is to use in the matching network an SP&T circuit, which at the end is a switch circuitry that connects a common input-output port to an output. Can be to this output or to this output, or even two at the same time. So let me show you two examples on how we can include these components in a matching network. In this first one, we have our antenna booster, we have the ground plane, we have a matching network, and we have our 50 ohm transmission line for testing purposes. And this black box here, which is this rectangle here, is a DTC, a digitally tunable capacitor, that is controlled through software through another lines that are on the bottom PCB that is connected by software. In a real life, this will be driven by the transceiver. The transceiver will be in charge of setting an state to this DTC. So let me illustrate an example. Let's imagine that this capacitor is at state 00, which is represented by the purple line. And the purple line shows high efficiency for 0.9 gig, okay, also here. But at 0.7 gig, efficiency is only 5%, okay? But if we change the state of this capacitor to another state, this is done obviously in a proper way. In this new stage of S27, you now see that the efficiency has been increased from 5% to almost 50%. So 10 times more, 10 dB more efficiency. So this ensures more range in your communication. So you can see that the tunable solution expand the efficiency and the bandwidth you can get with a passive solution in the case that your passive solution is not enough. Obviously, the cheaper solution is always the passive, but in those cases where you need connectivity and you cannot meet with a passive solution, then active solution is the best option. Okay, and yet another example. In this case, we have a very small device, only 50 by 50. Let's imagine that you want to embed this in a bicycle for having connectivity in the cellular domain. Since the ground plane is small, it's difficult to have enough bandwidth to cover all this cellular frequency region with a passive matching network. So instead, what we did, and this is a real device that this solution is implemented in hundreds of thousands of these devices, is the following architecture. We have the transceiver, okay, which is here. We have 1 and 2 switches, or let's call it single pole 8-throw switches, and we have several matching networks. So we have divide the whole problem by using a bunch of matching networks, single band matching networks, so only one or two components. So at the end, imagine we need to operate across this frequency region. Well, at this point, we have the antenna booster, the reactive impedance, we have a matching network. At this point, we have the 50 ohm. So this means we have 50 ohm, which is the input impedance of the transceiver. So if there is matching, then all the power goes to the antenna system and eventually goes into space. So at the end, if we need to operate in another frequency region, now you can imagine that the role of the transceiver through these control lines is to set a particular state so as to connect the input to this output to maximize the power delivered to the antenna booster system. Also for this case, we need to have GPS connectivity. So you can imagine, well, we receive the GPS signal very weak because it comes from a satellite. Then we have a matching network. This is 50 ohm at this point because we have an LNA, low noise amplifier. So the signal is not reflected because this is 50 ohm. Thanks to the matching network, the signal is amplified. This is again 50 ohm, 50 ohm. So now all the power is delivered to the GPS. So this is not only multiband, but multi-radio because we are combining cellular and GPS with the same tunable architecture. Just let me highlight or to show or emphasize the advantage of a tunable solution compared to a passive solution. So let's imagine the same device that we discussed before, 50 by 50 millimeter for cellular bands. What if we address this design with only a passive matching network? So we did it. Okay, we optimized the matching network, and here we have the results. In the vertical axis, we have the frequency, and in the horizontal, we have the efficiency. In gray color, we have the efficiency we obtain with a passive solution. Okay, only inductors, only capacitors. So, well, since there is no enough bandwidth, you have a trade-off. Okay, I'm going to have a good matching in this frequency band, but if I have a good matching in this frequency band, I cannot have a good matching in the other bands, then my efficiency is going to be very low. You can see the gray line, it's 15% and drops eventually to, well, 1%. This is very low efficiency. In the high bands, there is no big deal because in the high bands, the ground plane in terms of lambda, it's big. So typically a passive solution, it's very, very good. But in the low bands, in this case, it's a very critical situation if you want to have very good connectivity, or in some cases, imagine a bicycle that you need to ensure that the battery lasts for hours. If the efficiency is very low, then the amplifier has to pump more power into the antenna to ensure range. So this is going to drain the battery faster, which is also, again, no good, okay? But if we use a tunable solution, in this case, another architecture, we obtain always good matching across all frequency bands. And you can see in green color, it's the efficiency of the tunable solution that in this case, compared to the passive, it's the same because we have the same efficiency. But in other frequency bands, there is a very substantial increment of the tunable solution. The inconvenient, well, inconvenient, you have extra cost. You have a component that is a tunable component, 25 cents, it's okay. But, well, what if you use a passive solution that is very low cost, but at the end you don't have connection? Well, that is a disaster, okay? So sometimes, well, you have to invest in a perhaps more sophisticated or more, a little bit more expensive solution, but to ensure that you have connectivity and you are not going to have problems. Okay? Imagine that the bicycle has to be connected to the car and it has no connection. Wow, that can be a disaster. Okay? So just to highlight, if any of you is working in perhaps in AI or genetic algorithms or so on, in this slide, I'm just comparing the design of a matching network for an antenna booster through, let's say, artificial intelligence or optimization inspired in genetical algorithms and so on, and the design of a matching network by human or by engineering expertise or by experience. Okay, this illustrates our engineering suffering because it's 7-component matching network, trial and error, breaking PCBs. So after hours, even in some cases, even some days, to finally obtain the multiband matching network. In this case, you can see it's huge matching network, and the comparison with this, which is pure automatic, pure software driven, the one are more or less comparable, but in the high band it's much better the base on the machine. Okay, not only more efficiency, one component less, but it's time. This is a matter of minutes. This takes hours, even in some cases destroying PCBs, and 2 or 3 days to finally you end up with the matching network. And you don't know if that matching network is the best you can do. Perhaps you have a matching network and you finish your work and say, wow, but is this the best I can do? With the software, you know that typically if it's the code is well written, or the software, it's a good software, it ensures that you don't end in a local maxima, it goes to a global maximum, so you get the best. This is the best solution you can get, okay? So this means that, well, the near future or the close future, everything can be put in a robot, the simulation, the optimization of the matching network, even the building of the PCB. So this means that, well, robots will have a big opportunity to have work to do. And we as humans, for sure, we will have new things to do, but not those repetitive or mechanical things that can be easily transferred to a machine. Just to compare, because some of you say, okay, yes, but for my kind of V2X or smart city or IoT application, I also know other kind of technology. Okay, there are also very good technologies out there, but in my experience and in some workshops, I realized once that, well, FPC antennas. Okay, it's very simple because it's a piece of an antenna printed on an adhesive, plug and play, and well, you have the operation. But is this as nice as it looks? Well, the reality is not. An FPC antenna, it's efficient as long as you don't put the FPC on top of the PCB. I mean, you can get the FPC put far away of the PCB, and this provides very good results. So if you have a space in the device, okay, but imagine you want to integrate this in a bicycle, which is a tiny space, or a motorbike, or even a traffic light, and there is not too much space. So what happens that, well, typically you should embed the FPC on top of the PCB, which typically is a metallic ground plane. So what we did here, we compare the same PCB with an antenna booster on one hand and the FPC. You can see how big is this. This is more or less 90 millimeter. This is only 12 millimeter, okay? And we designed both systems to operate across cellular frequency bands, so 0.7, 0.9, 1.7, 2.7 gig. In red, we have the efficiency, measured efficiency in the anechoic chamber for the antenna booster, 70%, 70% so. And the other lines represents the FPC for several heights. So in this table, we have, for instance, the FPC at a height of only 2.4 millimeter, which is, by the way, the height of the antenna booster. When we put this FPC only at 2.4 millimeter from the PCB, the efficiency is very, very poor, only 1% compared to 50%. So 50 times more efficiency with the antenna booster, okay? Even if you put the FPC at a distance of 20 millimeters, so a thick kind of device, still efficiency has improved, yes, but it's still much less than the efficiency you get with the antenna booster. In the high bands, there is no issue because everything is electrically large and the efficiency we can get, at least when the FPC is in the thick scenario, I mean, in the 20 millimeter, efficiency is close to the antenna booster, but you can see in this table, when the FPC is at the same height as the antenna booster, it's only 10% when it's 65%, okay? I don't want to mean that FPC are not usable. No, FPC are very convenient, as long as you don't put the FPC on top of the PCB, which maybe in some cases you cannot do it, and if in some cases you can do it, okay, it's a very convenient strategy to follow. And finally, I don't know how much this is connected with V2X, but perhaps in the future we are talking now, cars are going to be connected with bicycles, with traffic lights, with parking sensors, with base station infrastructure, other cars and so on, people through a mobile phone. But why not cars cannot be connected with plants? Okay, we need to have our cities more populated with plants, trees, and so on. And in here, I'm illustrating a very preliminary project we are running at the European level called EcoSentinel. You can have some details here that we started this year. It's a consortium between University Ramon, my university, the company Ignition, as well as University Côte d'Azur, University Trento in Italy, and Côte d'Azur is in France, University of Genoa in Italy, and Planty, another company in the Netherlands. So in this consortium, our mission is to provide the connectivity to plants. So plants at the end can communicate to plants, or perhaps plants can communicate to cars, okay? Let's see, I mean, there is no use case behind this. Now it's a dream, it's a proof of concept, how we can leverage antenna boosters to connect plants with plants. So obviously we want to decrease the carbon footprint. So one of the main goals is to have very small PCBs, very small devices. But if we have small devices, since the ground plane is small, it's going to be challenged to have high efficiency. But we have some evidence right now that we can leverage plants to improve the efficiency when properly connected to a wireless device. So this is point number one, leverage the use of plant leaf to improve the efficiency of a small PCB when embedding an antenna booster. And second, since we don't want to use batteries into plants for ecosustainable reasons, we are going to extract energy from soil because there are some oxidation process that happens in soil that creates electricity, very tiny electricity, but this electricity can be captured, stored, and eventually when the plant need to connect to another plant or whatever, then it has enough energy. One of the goals we have in mind, it's not for connecting cars, but perhaps, I don't know, it's for having more resilient forests. In Spain, for instance, we're suffering a lot of fires this summer. Once there is a fire in the forest, once you detect, perhaps, well, there are a lot of square meters that has been burned. Okay, so if plants in somehow could talk one to each other in kind of a mess from time to time, plants can communicate if they are thirsty, or eventually if they are dying. If they don't communicate, something is happening. So this is maybe one of the use cases once we finish this project. But for now, our mission is to provide connectivity, and perhaps in the future, I don't know, if there are experts here working in V2X, may dream with a solution that with a use case that makes sense, or perhaps not, that makes sense to connect cars even with plants for, I don't know what kind of information or useful application we may have, okay? So let me illustrate. In this case, we have a small PCB, only 20 millimeter, with an antenna booster at the frequency of 900. Efficiency is 25%. because we have a small PCB. The PCB or the ground plane matters. But once we connect through, this is an aloe vera leaf that has high contents of water. This is what we believe impacts the efficiency, like enlarging the ground plane through a dielectric material. You can see the efficiency, how it improved from 25% to 50%. So it's a 3 dB improvement. So we are working in this line. Also, there are in the team biologists to ensure that, well, we don't damage the plants don't suffer, and which plants are more convenient to leverage the use of plants to improve efficiency. So this is in a very preliminary proof of concept, and eventually in the coming 2 years and a half, this will progress to a level that we can show that we can make plants talk one to each other. So that's all. Let me summarize. Antenna boosters are a simple and easy way to provide connectivity into your device, no matter if it's 0.4 gig, it's 1 gig, it's 2 gig, it's 3 gigs, 5 gig, any kind of protocol in this world of IoT, V2X kind of connectivity. Here are some real examples found in industry, thanks to the commercial application that we have the company Ignion. Here is a nice example of how the same antenna booster can be used for different protocols. This is for mobile, cellular communication, matching network, and to a transceiver. Another antenna booster for GNSS, so this means GPS, Beidou, GLONASS, satellite communication, matching network, and the transceiver. Bluetooth Wi-Fi, matching network, and to the transceiver. And this is a very nice example shared by a company from India, Rioche. We have also many customers from India that are providing connectivity through our antenna booster technology. So antenna boosters are small, single band, multi-band, multi-radio, cheap kind of components. So it's simple to pick and place into a PCB and ensuring quality. A lot has been done in this world of antenna booster, but still a lot is still to be done. So if any one of you is doing research, well, I invite you to research on this topic in whatever topic. You have my email. If you need my assistance, glad to provide some help. Well, I need to thank the European Commission for giving grants on this topic. Also, the Spanish Ministry through several funds, the CDTI, for all these fundings. I would like to express my gratitude to Professor Nagswar Rao for inviting me. All of you, I hope you find this presentation inspiring, interesting, and at least some of these topics, at least I will be happy in any of those topics is helpful for your research, or you engage with industry to provide connectivity through antenna boosters. I would like to share this link. If you go to Google and just write down virtual antenna MOOC, this is an open, free, 8-hour only open online course that you can do at your own pace. Very simple with 4 main blocks explaining what I have explaining today, with 90 very nice videos that it's not only useful for teaching. So if you are teaching and want to use for teaching, everything is open through these nice videos, but also for students, PhD scholars. And at the end, there is an exam, very simple exam that you can get the exam and get your diploma issued by my university, Ramon University, through the company Ignion. And then I think this can provide more knowledge about how to provide connectivity into wireless devices. Many people from India is doing this course and throughout the world. So I hope you find this course interesting. So go to Google, Virtual Antenna MOOC, sign up. I think you will love it. You will love it. For those of you who want to go deeply into this topic, we have this book that we published last year, Antenna Booster Technology for Wireless Communication. Plenty of exercises, divided in 4 learning journeys from, let's say, crash course, simple approach or beginners, kind of designers and experts, so different grades of learning. And well, it's 500 pages, but you don't need to read those 500 pages unless you want to be an expert on this topic. Well, I think you will love it. This is available through any kind of store, through Google or through the IET, the Institution of Engineering and Technology. So with that said, I conclude my presentation, and I hope you like it. Thank you.
Thank you, sir. Audience, any queries, participants?
Sir, you said like the booster device will provide wideband frequencies. So my question is like, will this drive many IoT devices with different frequency operation? And if so, will the IoT device respond automatically based on the corresponding frequencies?
If I understood, if you have a device that has to connect to, let me rephrase if I understood, because there is some noise in the background. If I understood your question, you want to know if I need to provide connectivity in a device through, let's say, cellular, Bluetooth, and GPS?
Yes, sir. Yes, sir. The same.
Okay. So, for instance, one approach will be one antenna booster per radio. This means, imagine you have cellular, narrowband IoT, or LTE, LTE4G. You have a transceiver. This is one chip. That chip has an input-output port, so you need to connect through a matching network to your antenna booster. In the same PCB, you have, or perhaps let me share my screen, and I think it's better to share my screen. Just hold on. I cannot share my screen. Yeah. Let me share again. Okay, for instance, in this example, we have connectivity in the mobile bands, okay? So we have one antenna booster, one matching network that goes to the input-output port. Then we want also to have in the same device connectivity to receive satellite signal, GPS. So we have another antenna booster in a matching network, and this goes to the input-output port of the transceiver. In this case, the transceiver has one input-output for cellular and one input for GPS. For Bluetooth, typically, it's a different transceiver. So you have the input-output for the Wi-Fi or Bluetooth. Then you have a matching network and a dedicated antenna booster for providing Bluetooth Wi-Fi connectivity. Okay.
Okay, sir. So one more question. If the matching network is increased or decreased, will it impact on the compactness of this antenna booster and to get our desired frequencies without any interference?
In increasing the complexity of the matching network, I mean, typically for single band operation, when I say single band is for GPS or Bluetooth and so on, typically the number of components you use is 2 or 3, okay? In some other cases, based on our experience for the most complex, which is cellular frequency bands, requiring a first frequency region and then the high frequency region, another region, typically you need to increase the number of components. And in that case, my experience tells that no more than 7 or 8 components should be used, because then if you have more components, then you are introducing losses in the system. So you are not improving the efficiency anymore. So from a practical perspective, yeah, increasing the number of components may help you in having more bands, okay? But also you have to be aware that, but this is something that the simulation can tell you, because in these simulations, in this simulator, sorry, that I was referring to, you can always challenge the simulator and say, well, what happens if, well, in fact, the simulator tells you the minimum number of components. If the solution can be obtained with 5, the software is not going to recommend 6 or 7. you can tell the simulator, give me the minimum number of components to achieve my solution. So this is really fantastic because you don't need really to think what happens if I put more components, because you don't need it. The software gives you the best you can do. I don't know if this is answering your question.
Yes, sir. Thank you, sir. How to manage the losses due to the RNG in this matching network? Resistance and conductance losses.
Yeah, of this. Typically, those components you can find in Murata, Colcraft, Worth. There are many TDK, many suppliers. And how do we know which component to choose, my inductor or my capacitor, in which figure of merit? Imagine a 5 nano inductor. You go to a 5 nano, you go to Murata, and 5 nano component, there are 20 different part numbers. And we say, well, can I choose any of those? The answer is no. You should look at the Q, the quality factor versus frequency. And in Murata, for instance, they have an application that is called Sim Surfing. It's an open tool that once you have a value of a capacitor or of an inductor, you can obtain the quality factor and choose the best quality factor. Okay, so if you don't choose the best quality factor, this will impact the efficiency of the matching network. But again, those simulators, they ensure that the components they put, they have the best quality because they maximize the efficiency. They don't maximize or they don't minimize the S11. They maximize the efficiency. So in order to do that, they choose the best components, which is the components having the higher quality factor. Okay, so quality factor is very important. Okay.
Thank you so much.
The larger quality factor, the better.
Yes, sir. Thank you, sir. Thank you very much.
Sir, one more question, sir. Sir?
Yeah.
Sir, can I ask a question, sir?
Of course.
Sir, here antenna booster, and it is going to boost the energy according to the perceivable concept, sir, or else the amplitude concept, sir. Amplitude boosting or frequency boosting, sir?
I'm not really getting your question. Perhaps can you rephrase it? I don't get your point.
Sir, the antenna booster, whether it's boosting the amplitude or frequency, if the frequency booster means it is matching the perceivable theorem, perceivable concept.
Okay, let me try to answer. The name booster comes because at the end the booster is not an antenna, or it's let's say it's a very very poor antenna. I mean, what matters is the ground plane. The ground plane is what really provides you the efficiency and bandwidth. So imagine you have something like this, which is a booster on a very small PCB. Okay, if the PCB is very small, then you will have also a low efficiency. If you increase the ground plane compared to lambda, then you are getting more efficiency. I recommend perhaps to have a look at the MOOC, at the Massive Open Online Course I was referring to in that link. Perhaps let me put in the chat, because in that case, because that will help. Okay, let me share through the LinkedIn. Through the chat. I will add now the link. Okay, so here is the link. Yes, here is the link in the chat. So if any one of you, it's to me, well, it's fantastic. Okay.
Thank you, sir. Thank you very much, sir.
Welcome.
Any other queries? Audience, any other queries?
Sir, regarding this green connectivity, will they place the antenna at its root, or is it really implemented?
Sorry, can you repeat
regarding this green connectivity antenna boosters? Like, is it really implemented?
No. This is proof stage. Okay. This is something that we started this year. Okay, so 7, 8, 9 months ago. So it's not yet implemented. Hopefully, in 2 years, 2 years and a half, this is implemented. So I will have more data to share with you, and perhaps we can have a session of green connectivity to V2X or whatever. But it's a proof of concept.
Okay, thank you very much, sir.
Welcome.
Audience, any other queries? Audience? Madam, you can conclude, madam.
On behalf of the EC department, I extend our deepest gratitude to Dr. Jaume Anguera for delivering an exceptional and truly inspiring session today. Your insightful lecture on antenna miniaturization, flexible printed circuit antenna FPC, and next generation design methodologies has broadened our understanding of modern antenna technology with AI and its critical role to trigger a thought to apply in V2X and beyond 5G communication systems. Your ability to simplify highly complex concepts, share real-world industry perspectives, and present breakthrough innovations that is the proof of concepts such as green connectivity with antenna booster technology has greatly enriched our FDP. It's really an inspiring idea. The clarity and depth you brought from fundamentals to cutting edge research have left a lasting impact on all participants. We are immensely grateful for the time you devoted to us, despite your global commitments, and for the knowledge, shared links, referred books, enthusiasm, and motivation you have shared with our faculty, researchers, and students. Thank you, sir, for your invaluable contribution. It was an honor to have you with us, and we look forward and pleased to have the opportunity to host you again. Thank you very much, sir.
Thank you very much. Appreciated. It has been an honor, and Danyabat, and all of you. Thank you for your patience, and let's keep in touch. Have a good Friday afternoon.
Yeah, thank you, sir.
Thank you.
Thank you.
Bye bye, guys. Bye bye. Thank you very much.